Good morning, everybody.
Good morning.
Everybody have a good weekend? I'm seeing some thumbs up. I'm seeing some yeahs. That's good. Glad you enjoyed your weekend. Thanks for coming back for week 2. We're going to get started in chapter 2 today. But before we do, we're going to finish up on some functional groups. Give you a little bit more on that. And then we're going to start talking about types of acids and bases. And acids and bases are probably the most important concept in chemistry. And unfortunately, in this class, we don't go into them in a lot of depth. But you'll see what I'll give you what you need to know in terms of acids and bases. The chapter's actually pretty short. We'll talk a little bit about equilibrium. We'll talk a little bit about what alters acidity, because as we get into some later chapters, you're going to find that a simple acid-base reaction can explain most of organic chemistry. A lot of what happens is nothing more than the reaction of an acid plus a base. So being able to know what alters that acidity and why something can become more acidic or less acidic depending on what's attached to the acid is really important. And then we're going to talk a little bit about basic reaction mechanism, okay? You will not completely understand reaction mechanism by the end of the day, and I don't expect you to, okay? That's not the goal. But we're going to start talking a little bit about how we push arrows and how we think about reactions occurring. In 106, you learned that a reaction occurs when two things bump into one another and a product forms, right? But how does that actually happen? How does A and B actually interact to form C? And we'll talk about that. And it has everything to do, as you might imagine, with the electrons. So we'll get into that as well. So, last time we finished up by talking about functional groups, very briefly, so I want to pick back up on that. Functional groups are one of, aside from acidity, are another important piece to organic chemistry. You need to know your functional groups by sight. And a functional group is a collection of atoms that have a particular function. A particular chemistry is expected from a functional group, okay? Now, you all have a few functional groups that are listed that I'm going to hold you responsible to for right now, which is what we're going to go through today, okay? But know that there are lots and lots and lots of functional groups, okay? The list is actually quite long, but we're going to talk about the most prominent and the ones that are probably the most important as you go into biochemistry, okay? We'll cover those, all right? The first functional group that you all need to know about is the alcohol functional group. It's the OH. Anytime you have an oxygen directly attached to a hydrogen, that is an alcohol functional group. What is R? R is anything that's carbon. Okay, it's just a generic representation for an organic molecule that happens to be connected to an OH group, okay? Or an alcohol group, or a hydroxyl group, some people call it, okay? Here's an example. This is menthol. It's a typical thing that people come into contact with, right? There's a lot of menthol flavorings and different things. Yes?
Is alcohol and hydroxyl interchangeable?
They are the same, they mean the same thing, yeah.
Okay.
An alcohol is what we name the molecule, but the hydroxyl group is the actual function.
So do we need to memorize the names of them? Do we have to just be able to see them and know them, or know their names?
You need to know their names too. In organic chemistry, we quite frequently just talk about functional groups. Okay, so you have to be able to identify them by sight, and you have to be able to know what the name is. You need to know that this is a hydroxyl functional group or an alcohol. Okay.
So both names, hydroxyl
Yep.
and alcohol.
Yep. You need to know both names. For this one has 2 names. Many of them don't. Okay. What does that look like? What other common thing that many of you are probably drinking right now? What else does it look like?
Milk and tea?
What's in milk and tea? Water. Alcohols are nothing more than organic derivatives of water. You all have heard of the term carbohydrate?
Yep.
Sugar, right? A carbohydrate is nothing more than carbon plus water. It has carbohydrate sugars have lots of OH functional groups. Hydroxyl functional groups, alcohols, okay? This is an example. So what is R here? R is all of this. This is R. and this is OH. Okay, so this is just all the carbon coming along for the ride. And it doesn't matter whether this OH is attached to this or something else, they all have the same type of chemistry. The alcohol functional group, I can convert that into other functional groups. Okay? That's all you need to know right now. But regardless of what kind of molecule it's in, they all have similar chemistry. Which is nice, because organic molecules can get really huge. So if you can break it down into the types of functional groups, you can really start to understand the chemistry. Okay? So this is menthol, comes from peppermint type plants. If you take a peppermint plant, you grind it up, you extract, you will get menthol. Menthol is used to be put in tobacco products. It's used to be put in throat lozenges. A number of things use menthol. It's a common molecule that is derived from nature, but it is an alcohol. Okay? Another functional group that you need to know about is the amine functional group. The amine functional group is a nitrogen that has its lone pair and is attached by single bonds to three other things. Those things can be carbons, or they can be a mixture of carbons and hydrogens. So R prime and R double prime can be the same, or they can be different. Here is an example of an amine. Okay, now note that the lone pair is not shown, but it's there, because we know that because there's not a fourth bond. Okay, but that nitrogen is bound to two hydrogens and a carbon. Okay, it is an amine. Okay, very important functional group, in fact. This is mescaline, which comes from this cactus kind of stuff. It's a psychotic drug. It's kind of related to methamphetamine, actually. Yeah.
Can you explain that a little more on where the NH2 is connected?
Here?
Yeah.
Okay, so that hydrogen, if I look at the Lewis structure, that nitrogen is attached to two hydrogens, and that nitrogen is also attached to a carbon. I can draw it out differently.
So that line is on that line where
This line is a bond to a carbon atom. These vertices are representations of carbon atoms. Okay? We'll learn a little bit more about that in the next chapter. But basically, all of this is R, N, H, H. That's what that representation means. Yes, ma'am.
Did you say all of the R's have to be the same thing?
Nope, they don't. They can be different. This is an amine. So let's just put something there. Let's make it real. That's an amine. That's called, don't worry about the name, but it's called methylamine. It's actually a compound that's controlled because it is actually used in the manufacture of methamphetamine. We won't talk too much about that. That is dimethylamine. It's got two CH3 groups, so again, don't worry about the naming. But it too is an amine. The nitrogen's attached to three different things and has three things, and a lone pair of atoms. I can also go and have nitrogen that's called trimethylamine. It smells like dead fish. Okay? Turns out that amines do have a terrible odor. Okay, you'll know if you're around an amine for very long, because they do stink. Okay, but that nitrogen with its lone pair of electrons is what makes all of the chemistry of all of these be about the same. Okay, so that's the amine functional group. Here we get into what's known as the aldehyde functional group. Okay, so we've got some organic thing, R, right, that's carbon, that's attached to this carbon, that's doubly bonded to an oxygen, that's also bound to a hydrogen. All of these atoms in blue are what we call the aldehyde functional group. Okay? C double bond OH. This is the aldehyde functional group. And you all are familiar with this. If you like cinnamon flavored stuff, they put this compound called cinnamaldehyde. Notice right there is the aldehyde functional group. Okay, so this odor that you smell from cinnamon comes from cinnamaldehyde. The flavor that you taste when you eat something that's got cinnamon in it comes from cinnamaldehyde. Okay. So now we've got functional groups that start to contain different types of bonds. This carbon is doubly bound to an oxygen and singly bound to a hydrogen. That's the aldehyde functional group. Yeah.
In R, whatever, as far as the bond goes, does anything that's there have to contain carbon?
R implies that there's a carbon there, yes.
Okay.
Yep. So this bond has to be between the aldehyde functional group and another carbon for it to be the aldehyde. If this were an oxygen, it would actually be a different functional group that we're not going to learn about. So anytime you see R, you need to know that that bond between R and carbon, or R and whatever atom of the functional group, that R represents at least one carbon atom. Good. No. We also have the ketone functional group. Notice it's that C double bond O again, but this time the carbon has no hydrogens on it. It's just connected to two R groups. Okay? In this case, the two R groups happen to be part of a ring, which we'll learn more about later. Okay? So this is a carbon atom doubly bound to an oxygen. This is the ketone functional group. Notice it has similarities to the aldehyde functional group. What are the similarities?
The oxygen double bound to a carbon, but ketones don't have the hydrogen.
That's right. Ketones don't have the hydrogen. They have two carbons that are attached to that. This C double bond O organic chemists call that the carbonyl group. And the carbonyl group, the C double bond O, can actually belong to a variety of functional groups. Okay? So it belongs to ketones, belongs to aldehydes. It also belongs in carboxylic acids. Okay, so here's an example, right? We've got carbon doubly bound to oxygen, that's the carbonyl group, but it's also connected to what looks like an alcohol, right? But all of these atoms together, it's not a carbonyl plus an alcohol, it's a carboxylic acid. It has a different function, okay? It actually functions differently than an alcohol would, or a ketone. It's its own unique chemistry. We'll learn about that in later chapters. That's called the carboxylic acid functional group. If you all like to eat salad with Italian dressing is oil and vinegar. The acidic component of vinegar is called acetic acid, and that is a carboxylic acid. So you all actually consume carboxylic acid. So this is what acetic acid looks like, just to give you an idea. Okay? It's what gives vinegar its smell. Regular white distilled vinegar, not any of the fancy ones that they put other stuff in. Okay, but just regular plain old vinegar. Acetic acid. Would you say that smells good?
No.
Nah, you wouldn't put it behind your ears, would you? I mean, it doesn't really smell good at all. Carboxylic acids have a very unique, nasty smelling odor.
And usually it says that behind your ears, where your scent comes from.
No, I meant that as a joke. It was about perfumes. What you wouldn't want to put a carboxylic acid on for a perfume because they stink.
One of the organs back of the ear, there's a gland back here that gives off hormones or smell.
I guess. I don't know. I'm not a.
Yeah.
Yeah.
It's right back here.
But you also take this carboxylic acids probably after you leave class and you have a headache. Right? If you take ibuprofen, you're taking a carboxylic acid. It's a very important functional group. If you remove this functional group from this molecule, it will not cure your headache. It has to be there. It has a particular function. Okay? So you got to have that if you want your ibuprofen to work. Here's another one that contains a carbonyl. This is called the ester. Notice it's a carbonyl attached to an oxygen, but that oxygen doesn't have a hydrogen on it. It's got another carbon. Okay, so just like we have here, carbonyl, oxygen, carbon. Okay, this is known as the ester functional group. Okay, the interesting thing about ester functional groups is they actually do smell good. Most of the stuff that you all put on for your perfumes and your colognes are esters. Flowers make these scents. Okay, this is known as methyl salicylate. Don't worry about the name, but it is the active component of wintergreen oil. Okay? If you've ever smelled wintergreen, you know it smells pleasant. Smelling vinegar doesn't smell pleasant. What's the difference between the ester functional group and the carboxylic acid? This has another carbon, whereas the carboxylic acid has a hydrogen, right? And so simple changes make big differences in how these things behave. Okay? And so smells good. I don't know if you'd want to put oil of wintergreen on for your perfume, but it smells a heck of a lot better than vinegar. I think everybody will agree with me, right? So that is the ester functional group. And then we also have what is known as the amide functional group. A-M-I-D-E, amide. When you all get to biochemistry, they're going to call this a peptide bond. When you get to biochemistry, they will call an amide as a peptide bond. It's how amino acids come together to form proteins and peptides, important biological molecules. But they are composed of amide bonds, and we'll learn a little bit about that at the end of the semester. What does this kind of look like? It looks like we've taken a carbonyl and an amine and stuck them together, right? That's kind of what it looks like. Okay? And so it's these three atoms that make up the amide functional group. Okay? Here's an example of LSD. Okay? I picked some of these examples because some of you are in forensics, right? Good examples to have. LSD has an amide functional group. It's even in the name, lysergic acid diethylamide. Okay? Pointing out that that functional group is needed for it to have the LSD effect. Okay? What other functional group can you readily see in LSD that's not pointed out? Yeah, there's an amine. I'm sorry, it never does show up on the TV. There's an amine right there. Is there another one? Right down there at the bottom, right? So lysergic acid diethylamide has an amide functional group. It's got an amine and another amine, and it's got other functional groups that we're not learning about yet. Okay? So don't worry about them. But you can clearly see that it's got the amide and the amine functional groups. That's the cool thing about functional groups. Once you know how they behave, you can start to think about how molecules can be built up containing multiple functional groups, and how you can start to design molecules that have particular properties. That's what Mother Nature's done. Mother Nature's taken simple organic molecules that she refers to as amino acids, puts them together in unique ways to make proteins and peptides. The protein in your muscles is different than the proteins in other parts of the human anatomy, right? And so you can take the same kinds of things, mix them together differently, and get unique properties. All right, so I want you all to take, let's do about 5 minutes. You all get in pairs, no more than 3, okay? But pair if you can. And look at this complicated molecule. This is Taxol. This is the molecule that is so useful in treating both breast and ovarian cancer. Okay? See if you can identify some of the functional groups that we've already talked about. So pair up with somebody. Don't worry about drawing it out. Just see if you can come up with the various functional groups, and then we'll go through it. So take 4 or 5 minutes.
Very smart people in the lab. If there were 5, this would be treated as cancer. Right there. Right,
Gotcha. That may just not be something you have to be over. Or something. I've heard of the way Sylvia.
Bless you. Well, bless you your way.
Just because he said we're gonna get into the nail and stuff, but. I'm a big person, so put together. I make except for the last one, yeah, those are two that I can't lost. That's like that.
You're looking at just the wage group thing?
So we're gonna need to go website by name.
It is. That's what I'll show you why.
I'm never gonna draw something like that. Oh yeah, I didn't draw that one. I literally just that was no. Like that's I think talks or something like that. Unless I write super tiny.
Okay. Let's wrap up with our pair and share, and let's look at this complicated molecule. Interestingly enough, like it says, this comes from the Pacific yew tree. It was found in the bark. You can find precursors to it in the needles. Very potent ovarian cancer drug. Pretty good, I think, breast cancer drug. Saved a lot of lives, but to treat just a handful of people, we would have had to decimate the forests. So organic chemists actually had to figure out, once they knew what this compound was, they had to figure out a way to make this from things like crude oil. Okay? And that actually, back in the 90s, was a big thing in academia. People were trying to figure out an efficient few-step synthesis to Taxol, because the more steps you have, the more expensive your drug becomes. And this is a more complicated molecular structure than you all can know at this time. It's more than just its functional groups. Okay? But its functional groups are certainly very important. So let's go through and see if we can identify some of them that we know, right? Anything on this side? What do you see?
Amides.
Okay, so we see an amide. We see an alcohol or a hydroxyl, right? What else do we see?
Carbohydrate.
We see an ester. Yeah. What else do we see? What about over on this side of the molecule?
Another ester.
Yeah, we see another ester.
Oh, so wait, so we don't call them the name of the group, we call them the president.
Like what?
So we don't call them the group, we call them what the president?
I don't understand the question. We name them just by the functional group right now.
Oh, okay.
Does that make sense?
Yeah.
Okay. So here we have an ester. We have a ketone, right? What else do we have over on this side of the world?
Alcohol.
Okay, we have another alcohol or hydroxyl group, right? What about down here at the bottom?
Another.
There is actually two more esters, right? There's one right there. There's one right there. What else is there?
Alcohol.
Another alcohol, right? This is a functional group. It's called the ether, but we haven't held you responsible for it, so don't worry about it. This is also a functional group called an alkene, which we'll learn about in chapter 4, but don't worry about it yet. Okay? Yeah.
So do you want us to memorize just the ones that we just went over now, or all the ones we've done?
I want you to memorize the ones that we've gone over now, and we will learn the other ones as we need to. Yep. Yep. So no need to get too far ahead. We'll introduce new ones as needed, but right now, these, what is that, five functional groups? 4 or 5 functional groups are the ones that you absolutely need to know. 7, actually? I'm way off in my numbers, aren't I? You need to know all 7 of those for everything we do from now on out. Those are going to be very important. Okay? All right, let's switch gears just a little bit and get into chapter 2. There are 3 types of acids and bases. And you'll see that I have used a little different font size for all of them, indicating what I think are important about all of them. Okay? There are Arrhenius acids and Arrhenius bases. There are Bronsted-Lowry. Oh, and I misspelled that. I said Bronsted. It's Bronsted. There should be an N there. Lowry acids and bases. And then there is the Lewis acids and bases. And I put that in the big. Lewis acids explain all of the others. I really don't know, other than for historical reasons, why we even bother to teach people about Bronsted-Lowry and Arrhenius. Because Lewis takes care of everything. But in their wisdom, when they write books, they feel the need to give you 3 definitions of acids and bases when one will do. Excuse me, I got something in my throat.
Do we actually have to know all 3 then, or should we focus on the Lewis one?
You need to focus on Lewis, but you need to understand that all 3 exist. Yeah, they're just different ways of thinking about the same thing, really. Excuse me. So, Arrhenius acids and Arrhenius bases, this came back from long ago. Anything that you take and place in water, if it generates the hydronium ion, H3O+, it was called an Arrhenius acid. Okay, so if you took sulfuric acid and you dissolved it in water, what happens? It dissociates and it forms hydronium ions, H3O+. Don't worry about how that happens yet. Okay? It is an Arrhenius acid. Okay? An Arrhenius base was anything that you dissolve in water and it forms hydroxide ions, OH minus. So sodium hydroxide, if you dissolve it in water, it makes OH minus. Okay? It is an Arrhenius base. That was Arrhenius' definition. If I put it in water and it makes H3O+, it's an acid. If I take it and I put it in water and it makes OH minus, it's a base. The problem with that theory is it only involves water. Water has to be the solvent. Most of what we do in organic chemistry ain't done in water. Okay? Now, in terms of biochemistry, most of what you'll do is in water. Okay? But Arrhenius is just a subset of acids and bases under very special conditions. Bronsted-Lowry expanded that a little bit. So basically the Bronsted-Lowry theory was anything that donates a proton, H+, is an acid. And anything that accepts a proton is a base. Okay, we'll see some examples on the board in a minute. So what's the focus of the Bronsted-Lowry theory? The proton. Well, when we get into some organic chemistry, we realize that there are things that act like acids and bases that have nothing to do with protons. So it doesn't explain everything again. Then comes along G and Lewis. Lewis structures, Lewis acids and bases, it's the same Lewis. It's the guy who should have won a Nobel Prize that didn't.
He was too spited.
He was not liked by his colleagues, apparently.
That's what we're not like.
Yep, he was not liked by his colleagues, apparently. Should have gotten a Nobel Prize, in my opinion, okay? Because we talk about his name all the time, okay? Lewis acids and Lewis bases. And Lewis decided, you know what? And I'm just making up words, and I don't know what he really said. But I would, if I was Lewis, this is what I would have said. We're chemists. We deal with electrons. Why are we talking about hydronium, hydroxide, and protons, which have no electrons, right? We're chemists. We deal with electrons. And so Lewis came up with the definition of an acid as being anything that accepts a pair of electrons. It's an electron pair acceptor. And he said a base was anything that donated a pair of electrons. There are electron pair donors. Now, if you look at Bronsted-Lowry and Arrhenius, you find out that they are all Lewis acids and bases. So the theory that Lewis came up with explains everything else. We'll see some examples of that. Okay? And so, for some reason, in the textbooks, we like to tell you all about all three, when really all we need to focus on is the one. Right? But as you get into biochem and you get into other things, they will talk about, and they might use different language. So we want to make sure that you're at least familiar with all three of the most commonly accepted theories on acids and bases. So here's some examples.
So the electron pair acceptor is the base?
The electron pair acceptor is the acid. Yeah. The electron pair donor is the base. So here's an example of some reactions. If I take an acid, in this case the acid is water. Water can be acidic. Okay. You can think of it as an acid. And I put it in the presence of a base. This base is NH2 minus. It's a very strong base, by the way. It's called amide, spelled the same as amide, not to try to confuse you, but you pronounce it differently. This is the base. This is the acid. Okay, so the acid gives us the conjugate base, and the base gives us the conjugate acid. Notice what's happened. This has accepted a proton. Remember, a proton is nothing more than a hydrogen atom, right? Without its electrons, right? So this has two hydrogens attached. Now it has three. It gained that proton. Okay? So it's the proton acceptor. This gave away one of its protons. Okay? So it's the acid. Okay? So the acid always gives you the conjugate base, and the base always gives you the conjugate acid. What are these arrows trying to tell me here?
That's
That pair of electron went to that.
essentially
Yeah. Okay.
that element went to that way.
Okay, so let's draw this out actually, and let's give it a little bit of real structure. Not flat. I'm just going to make that the minus, right? So this nitrogen's attached to those two hydrogens. Okay? What you're seeing in those arrows is what we call the reaction mechanism. Reactions occur because electrons make everything move. Okay? It's what does the chemistry. What do we know about the oxygen-hydrogen bond? Is it polar, nonpolar, covalent, ionic? What is it?
Covalent polar.
Polar covalent. Why is it polar covalent?
Because oxygen is more electronegative than hydrogen.
That's right. So this is more electronegative. This is more electropositive. And we use a little Greek symbol delta. Okay, so it's got a dipole, right? So these electrons in this bond, are they equally shared or unequally shared? Unequally shared. And where are they spending most of their time? Close to?
The oxygen.
Close to the oxygen. Right? So that means that the hydrogen would like to have some more electrons, right? Because it's kind of deficient. Where can it get them? It can get them from the base. The base has a lot of electrons. In fact, it's negatively charged. Not all bases are negatively charged, by the way, but this one happens to be. Okay? And so how we think about this, right? So one of these lone pairs of electrons will move, and as they move, the whole thing moves, okay? And we use a double-headed arrow indicating that it's an electron pair. 2 fish hooks, if you will. 1 fish hook for each electron. It's important that you draw the right arrow. How many bonds can we have to hydrogen? We only have 1. So I'm forming a bond between the nitrogen and the hydrogen, but if I do that, I would have 2 bonds to hydrogen, right? So what has to happen?
One must break.
One must break. And it's this one, right? And what happens to these electrons?
Become a lone pair.
They become a lone pair on oxygen. And that makes sense because oxygen's already pulling those electrons close to it, right? This is the basics of a reaction mechanism. Most organic reactions can be thought of as nothing more than a Lewis base reacting with some type of Lewis acid. You're going to see that theme over and over and over again throughout the semester, okay? And so we end up with the conjugate base, and we end up with the conjugate acid. What does the arrows in between mean? What do these arrows mean? Okay, reaction, a little more there.
It goes both ways.
It does go both ways, right? I mean, it can also go in reverse. This is what we say, it's an equilibrium, right? This is an equilibrium reaction. Now, we don't know whether the equilibrium lies to the right or to the left yet, but eventually we'll be able to make that prediction based on the types of acids and bases that are involved. Here's another example that's actually more organic-y, if you will. What functional group is this?
Alcohol.
That's an alcohol. This is called methanol. Don't worry about the name. It's wood alcohol. It's the kind of alcohol that if you drink, you go blind. Okay? It's the kind of alcohol that if you buy moonshine from somebody that doesn't know what they're doing, you go blind because they end up making more methanol than ethanol. Okay?
Oh, that's true.
It's very true. Yeah. That's one of the reasons why making
Moonshine.
moonshine is illegal. You can cause people serious harm if you don't know what you're doing.
Tell that to the application Mounties.
Huh?
Tell that to the application Hillbillies.
Okay.
I got jokes today.
Okay. So, this is going to function as the base. HCl, you all learned about in Gen Chem. It's obviously an acid, right? This is the mechanism of what happens. So, methanol will react with hydrogen chloride to make the conjugate base chloride anion and what we call the oxonium ion. Don't worry about that name, okay? But it's just protonated alcohol. So it's ROH2 and oxygen has a positive charge. Why does oxygen have a positive charge? From the formal charge calculations, right? Everything on the left is neutral, so everything on the right must be neutral when I look at it together. So I've got a plus and a minus. Plus and minus add up to nothing, right? So I've got nothing. I got 0 charge on the left. I've got 0 overall charge on the right. Okay. This is the base. This is the acid. This is the conjugate base. This is the conjugate acid. Okay. This is actually a step in quite a few of the reactions that we'll learn about with alcohols later in another chapter. Okay. So they can function as bases. You have a table in your book. I do not expect you to memorize the table of acids and their strengths, but I do expect you to memorize rough ranges. You should know what are strong acids and you should know what are weak acids. You should know kind of what are strong bases and what are weak bases. And we'll learn that as time goes on, okay? But what you'll see is as we go down here, we go to pretty weak acids. Alcohols aren't very strong acids. Water's not a very strong acid. Hydrogen cyanide's not a very strong acid. But as you start to move up, right, now we start to get to acetic acid. That's relatively strong. Okay, it's much stronger than any of these things. There's nitric acid, sulfuric acid, hydrochloric acid, hydrogen iodide. All of those were strong acids. Okay? So, kind of know what are, if you look, the really strong acids are not organic. All of the organic things are kind of in the middle of the range or even weak acids. So organic molecules typically are weaker than things like HCl and HI. The conjugate bases, okay, notice that the iodide anion is a weak base, whereas the ethoxide ion, which is this, which is the conjugate base of ethanol, is actually a very strong base. So what does this mean? Strong acids result in weak conjugate bases. Weak acids result in strong conjugate bases. That's what you really need to know. If you go, hey, I've got a weak acid, its conjugate base, you would know it has to be a stronger base. And that makes sense, right? Strong bases want to react. Well, they don't want to form, they want to react. Well, a weak acid doesn't want to dissociate either, right?
Yeah.
So, kind of opposite sides of the same coin. Again, I don't expect you to memorize this table, okay? Now, these kind of tables are kind of useless, actually. Right? Just rough ordering. What's really important is knowing how strong an acid is and being able to determine how strong an acid is, okay? The way that we determine acid strength is by its equilibrium. What happens when we throw it in water? If it completely dissociates, it's a strong acid. If it doesn't dissociate very much at all, it's a weak acid. Okay? But we have to talk in numbers. Chemists like numbers, right? I like to know exactly where that is. So let's look at the general reaction of HA, where A can be anything. Okay, so this is going to be the acid, and we're going to use water as our base. So I'm going to dissolve HA into water. So I've got a little bit of HA, I've got, let's say, a liter of water, and I'm going to pour that HA into the water. Okay? It's going to set up an equilibrium where I end up with the conjugate base of the acid, and I end up with a hydronium ion, H3O plus. Okay? Now, if I'm in the laboratory, I've got this solution, I've got tools that I can determine the concentration of this, and I can determine the concentration of this very easily. I can do titrations. You all did some titrations in 106 probably, right? I've got instruments that can actually make these determinations for me. I've got lots of cool tools that I can use. We don't need to worry about what those tools are right now. But the thing is that once I know these values, I can determine what's called the equilibrium constant, Keq. And you all need to know that the equilibrium constant is always the products over the reactants. Always. Products over reactants. Well, what are the products of this reaction when I poured the HA into the water? The products are the hydronium ion and the conjugate base, A minus. They're at the top. So if I can determine H3O, I can by definition know what A minus is, right? Because this is 1-to-1 by stoichiometry. So if I use my fancy little tools and I determine, it's actually a pH meter, right? So if I use my pH meter and I determine the concentration of this, I automatically know the concentration of A minus as well. Okay, a little math there. So that's the products. And the reactants, or starting materials as they call them here, are HA and my solvent, water. Okay, so Keq for this reaction is equal to H3O plus times A minus divided by HA times H2O. If this number is really large, what does that mean? Pardon? Product favored. That means if that's really large, let's say it's 10,000, that means that almost everything is products and very little of it remained as starting materials. We would say that that reaction went to completion. What if this number is really low? Let's say it's 0.0001. We would say that the reaction didn't occur very well, right? And most of it stayed as starting materials. That's right. Why is that? Because if I have a big number here and a small number there, that has to be small. If I have a huge number here and a tiny number here, that has to be big, right? Just some simple government math gets you through this, right? We don't really need to get out a calculator with anything on this yet, okay? You need to understand the concept. So large values of KEQ favor the products. Small values of KEQ favor the starting materials, okay? That's an equilibrium. And it turns out, in large part, I think it turns out this way because back in the day when they started developing all this, there was no such thing as a computer or a calculator. And dealing with numbers that you're going to get from KEQ just was inconvenient. Right? I mean, can you imagine writing 10,000 or 10 million, having to write that down all the time, or 0.000001 or something like that? It gets monotonous. And so chemists don't actually look at KEQ. We look at what's called pKa, and we'll talk about that in just a moment. So we're going to derive from the equilibrium constant what a Ka constant is. Okay? Ka constant is called the acidity constant, and it's related to KEQ, but it's a little different. What's different about what's written up there versus what we've written up here?
The H2O is not there.
The H2O is not on that side, is it? Okay. You might have learned in high school, and you probably would have learned in 107 if you'd gone through 107, that water falls out of the equation. That is utter and complete nonsense. Water didn't go anywhere. Water's involved. Okay? But we can make an assumption about water. Notice that Ka is equal to KEQ, right, times the concentration of water. Right? Just doing a little arithmetic. Okay? Why can we do that? Why does it make sense to do that?
Because it balances it out.
Mathematically, you're right. Both sides of the equation are the same now, right? What we do to one side, we can do to the other. Well, what did we do to this side? We took it times H2O. What do we do to this side? We take it times H2O. That cancels out, and you end up with Ka, right? But why can we do it? Just because something can be done mathematically doesn't mean it makes any sense in the natural world, or it doesn't have to make sense in the natural world. Why can we do this? What do you know about water? It can be an acid or a base. That's a true statement. What else do we know about water? Is pure water concentrated or dilute?
Concentrated.
Very concentrated. If you took a liter of pure water, and I don't remember the exact number, but it's around 56 molar. Think about what you were dealing with in general chemistry. You were typically dealing with things that were 1 molar or less,
Yeah.
right? And you called those concentrated. But pure water, when you drink it, it's 55 or 56 molar. I forget the exact value. So if I add a little bit of HA to the water, am I really going to change the concentration of water to any great degree?
Not really.
No. It's the same thing as having your water bottle standing on the pier down on the coast, and your water gets hot, and you're like, I don't want that anymore, and you pour it in there. You don't say that you automatically diluted the ocean, right? You added very little to a huge pool. You made no, the sea level didn't rise because you did that, right? The same thing here. Since we're doing very little to the water, we can assume that it remains constant. And that's why we can do what we just did. And so Ka is equal to KEQ times water. And so that means that it is equal to H3O plus A minus over HA. So again, if Ka is big, what does it mean? Strong acid or weak acid?
Strong acid.
Big?
Strong. Pardon?
If it's big,
If it's big.
strong.
It's a strong acid. So large values for Ka mean strong acids. Tiny values for Ka mean weak acids. Okay?
So basically what we did was remove water from the equation right there?
Yep.
Because there wouldn't be a significant difference for us to account for it?
That's right. We can make the assumption that water didn't significantly change, and so we can do what we just did. Okay? This only works for dilute solutions of acid, which is what we deal with 99.9% of the time. Okay? If you take some additional chemistry classes later on, you'll learn that what I'm telling you right now is just a little bit of a fib. Okay? But it's a fib that works really well. Okay? It's a fib that works really, really well.
Fibs never work unless something goes wholly right or wrong.
So if you think about typical organic acids, the Ka values for just about any organic acid is going to be relatively small. Something like 10 to the negative fifth or 10 to the negative 50th. Remember, 10 to the negative fifth would be 0.00001. 10 to the negative 50th would be 0.000000000, you know, on out to 1, right? Lots of zeros there. Nobody wants to write that junk down on their paper or work with those types of things. So what we do is we take the negative log of that number and deal with numbers that we are more easily interested in. So if I take the negative log of those two numbers, the negative log of 10 to the negative fifth is 5. The negative log of 10 to the negative 50th is 50. So when I look at pKa values, the smaller number belongs to the stronger acid. It's exactly the opposite of what you would think from the KEQ, because we've taken the negative log of that number. Okay? That smaller number actually has a bigger KEQ. This big number actually has a smaller KEQ. Okay? So that's something that you've got to know. Small values for pKa are weaker acids, or excuse me, stronger acids. See, I have to think about it too. Bigger values for pKa are weaker acids. Okay? In mathematics, you can P anything. I know that sounds weird, all right? But you can. P just means to take the negative log of something. It's a function. So pKa is taking the negative log of Ka. What other P have you learned about in chemistry, previous chemistry classes? pH. You're just taking the negative log of the hydronium ion concentration. pH. pKa. You can do pKeq if you wanted to. You can P anything. Okay? It just means to take the negative log. And what it does is it gives us an easier way to handle numbers. I would much rather deal with 5 and 50 than 10 to the negative 5th and 10 to the negative 50th. Okay? Yep. All right. So let's go through this. Let's recap just a little bit. Okay, so Ka implies the concentrations of the acid and the ions that are formed, right? Tells us something about the position of the equilibrium. If Ka is greater than 1, I know that this is bigger than this. I have more products than reactants. If Ka is less than 1, I know that I have more of this than I do this. Okay? So if I had the pKa of 5, I know I have more products forming than if I had a pKa of 50, right? Again, keeping that in mind. If, however, Ka is much greater than 1, and we typically draw the line at about 1,000. That's what 10 to the 3 is. Okay? So if Ka is greater than or equal to 1,000, we say the reaction goes to completion, that there is no starting material left. So if you take hydrogen chloride, HCl, and you pour it into water, it completely dissociates into its ions. It has no HCl remaining. Okay? It goes to completion. And we also say that if it's about less than 1,000th, that we say that the ionization doesn't occur to any appreciable amount. Okay, so we have all starting materials and no, or very few products. Okay? Again, some general things that you need to know, be able to roll off with. All right, so here's a table. This isn't in your book. This is from another book, but I wanted to give you some examples of acid strength with some common acids that you might be familiar with. Hydrogen chloride is the acid that you all used in Gen Chem a lot. You used HCl to do titrations and do all kinds of stuff. It has a pKa of -7. That's a really tiny number, right? It's below 0, right? So is that a strong acid or a weak acid? Strong, and not only strong, very strong, right? This is acetic acid. This is that component, acidic component in vinegar. Its pKa is 4.8. It's positive. Is it a strong acid or a weak acid? Relatively. Acids and bases are about relative. It depends on what you're talking about. I know that's what drives a lot of students crazy. You all want definitive answers. But 99.9% of everything in life is relative. Okay? There are very few things in life that are absolute. It depends, right? It's just like money. If you have $1 million, are you rich? Not if you have $10 million in debt. Right? It's relative. Okay? So, this is water. 15.7 is the pKa for water. Is water a stronger or weaker acid than acetic acid? Weaker. Right? It's got a bigger pKa value. Right? Is it a little weaker or a lot weaker? A lot weaker. Remember, every unit of pKa, because you're taking the negative log, is like 10 to the 1. Right? It's tenfold. So a difference of 1 is tenfold difference. Difference of 2 is 100-fold difference. Well, if I subtract those two numbers, that's a lot of folds, right? Let's just call it that. This is alcohol, ethanol. This is what y'all like to drink. It's what I like to drink on a Friday night, okay? It has a pKa of 16. The functional group here is the OH functional group, or the hydroxyl functional group. What can we say about the acidity of alcohols with respect to water? About this, they're fairly similar, right? Remember I told you that alcohols were nothing more than organic derivatives of water? You're starting to see that play out here, right? We just took one of the hydrogens off of water and replaced it with something that's carbon. This is an alkyne. This is acetylene. We'll learn about that functional group later. Don't worry too much about it, but notice the pKa of that hydrogen is 25. Hydrogen is 35. Ammonia, this NH is 38. So what's happening as we go down? Are we getting stronger or weaker as acids? We're getting weaker. So what about the conjugate bases?
Stronger.
Much stronger, right? In fact, CH3 minus you can get, and it's, some people call it a super base. It will extract a proton, it'll do it from just about anything, okay? It has a pKa of 50.
So when they subtract hydrogen, they become bases?
Yep, that's right. The acid gives off a conjugate base.
Interesting.
Yep.
I just want to point it out.
Yep, it's a good observation. Now, obviously, when you look at this, not everything has the same acidity. So what is it that goes into making HCl different than acetic acid, that makes acetic acid different than water, that makes water different than some of these other functional groups that you'll learn about later? It's about what's attached to it. Okay? And the general rule that you need to know, it's that first box. Anything, and I do mean anything, that can stabilize the conjugate base, A minus, will make that acid more acidic. Anything. And think about that. Why should that make sense? Why should that make sense? If I have HA, which we just had up there, plus water, we'll set up an equilibrium, right? We get A minus plus H3O plus. And I just told you that anything that stabilizes A minus will make that acid stronger. Why does that make sense?
Repeat the question.
Why does stabilizing A minus make HA a stronger acid?
Because it's negative.
partially true.
Cause it just, I guess, I don't know.
What does it mean to stabilize something? Does that mean to make it more reactive or less reactive?
Less
That's
reactive.
All right. So in nature, you think nature wants to move towards things that are more reactive or less reactive?
Less reactive.
Less reactive. It's just like people, right? We try to find the lowest path to everything. We try to take as much vacation time as we can and enjoy our hammocks and things, right? All right, so you can think of it as kind of laziness, okay? But anything that can stabilize A minus is going to make this more favorable, which is going to push the equilibrium in this direction, okay? So anything that I can do to stabilize that will give me a stronger acid. Now, of course, A can be just about anything, right? And we'll talk about that as well.
What do you mean by stabilize A?
So to stabilize something, again, it means to make it less reactive.
So would that change, like, it's positivity or negativity?
It could change the overall charge a little bit, yeah, that's possible.
So would the stabilizer count as a catalyst toward?
Not a catalyst. A catalyst is a very special word, we don't want to use that here.
Okay.
Okay? This is all about thermodynamics, we're not going to get into all that. Okay? We just need to focus on the top part of it, which is anything that we can do to make this more stable, it's going to favor this.
Okay.
Okay? And there are 4 things that can do that. You need to know these by name. There's the element effect. There's the inductive effect. There are resonance effects. And there are hybridization effects. Those 4 things can be applied to A minus
To make it more stable?
to make it more stable. Okay? And you also need to know that no matter which factor is applied, the procedure is always the same. You're always going to set up some type of reaction like this. Okay, we'll do some examples. You're going to look at A minus and you're going to determine, is A minus more or less stable than some other A minus? It would be fair game for me to give you 2 acids and not a table and say which one is the most stable or which one is the strongest acid. This is how you would determine the strength of an acid. The relative strength, not the absolute strength of an acid, okay? The more stable the A, the stronger the HA, okay? That's the take-home message here.
And if A is more stable, then is that the conjugate base?
It is, the conjugate base. So the more stable conjugate base will come from the stronger acid.
Okay.
Yep.
So the initial acid would be stronger if the conjugate base
Is more stable.
is more stable.
You got it. You got it. So let's look at the element effects. And this is coming out of the periodic table. And I wish we had a periodic table in the classroom. We don't. But you can look in your periodic tables if you got them. So we're talking about the elements carbon, nitrogen, oxygen, and fluorine. They are on the second period of the periodic table, right? So we're going carbon, nitrogen, oxygen, fluorine. What do we know about the acidity as we go from left to right in the periodic table within a period?
Increases?
It increases, and I know that because I go from a pKa of 50 to a pKa of about 38 to a pKa of about 16 to a pKa of about 3.2. As I go in a period, let me draw it out. As I go in a period, carbon, right? Nitrogen, oxygen, fluorine. As I go from left to right, I increase the acidity. Why is that?
Does it have to do with electronegativity?
It does. So what I have to do is I have to look at the anions, right? I have to look at A minus. The A minus here is carbon with a negative charge. A minus here is nitrogen with a negative charge. Here it's oxygen with a negative charge, and here it's fluorine with a negative charge. Carbon is less electronegative than nitrogen. Nitrogen is less electronegative than oxygen. Oxygen is less electronegative than fluorine.
So the more electronegative, the more acidic?
Yeah. Why is that? Because A minus is more stable here than here. Fluorine's very electronegative. It pulls electrons very close to itself. As you're pulling electrons really close to yourself, you're pulling them closer to the nucleus. What's in the nucleus? Positive protons. If I take a negative and a positive and put them close together, that's stabilizing. Okay? This is more stable than this is more stable than that's more stable than that. So HF has a pKa of 3.2. Whatever this one is, this is some alcohol, right? Has a pKa of around 16. Some type of amine will have a pKa of around 38. And in this case, let's just call it methane, CH4, has a pKa of around 50. Yeah.
It's in our book.
They don't break it down in the language that I'm using here. I think this is easier language, but yeah, you can find, they talk about this just from electronegativity effects.
Are you trying to say that when they're pulling it for like fluorine and pulling towards the protons, are you talking about the electrons on the outside?
I'm talking about that within that bond, yeah.
Trying to stabilize it?
Mhm. So I've got electrons on fluorine, right?
Yeah.
And a negative charge. And that is going to be closer to the nucleus, it's going to be more stable than it is on carbon. All of these have lone pairs and negative charges. But the negative charges are on different atoms, and those atoms have different electronegativities. Okay? Does that make sense? Okay. Now, that's going across. But what happens as we go down the periodic table? Fluorine, chlorine, bromine, iodine. What happens as we go down the periodic table?
Get stronger acid.
You get stronger acids yet again. But guess what? Fluorine is more electronegative than bromine.
Yeah.
So why is it? What happens as we go down the periodic table? The atoms get bigger. Okay? So bromine is large, fluorine is tiny, or fluoride is tiny. So I put a negative charge on a tiny thing, or I could put a negative charge on a big thing. Why would putting a single negative charge on a big thing be more stable than putting it on a tiny thing?
Doesn't affect it that much.
Well, I go from a pKa of 3.2 for HF to a pKa of -9 for HBr. Weak acid, strong acid.
So when you go down the periodic table, it gets stronger acid?
It does. Why is that? It has to do with the size of the anion. So, I can't tell you the real reason. You'd have to learn that in physical chemistry. Okay? But just think about it as taking a negative charge and distributing it over a larger surface of a sphere. Okay? It doesn't crowd itself as much. Okay? It's more diffuse. Pardon?
Is it like the whole water thing that you said before?
Kind of, yeah.
Because it's bigger, so it affects it less, so it's more stable.
More stable, that's right. Br minus or I minus are more stable than F minus. And it has to do with how water interacts with it. We don't need to get into all that.
So
Okay?
is it the bigger the atom, the more stable it is?
Yep, that's right.
So it's got more surface area.
Yep, it is more stable. Okay? And here's the example, right? So as I go in this direction, HF has a pKa of 3.2, HCl -7, HBr -9, HI -10. HI is the strongest acid in that series. In fact, HF is only 10-fold greater in acidity than acetic acid. Okay? It's pretty close. It's still weak. When you dissolve HF in water, it doesn't completely dissociate. But you dissolve HCl, HBr, and HI, and they completely dissociate in water. Okay? You probably learned that HF is a strong acid. You learned wrong. It's a very dangerous acid. HF will eat your flesh. It will get in your bones and dissolve your bones. If you've ever watched anybody here ever watched Breaking Bad? Y'all probably, okay. How did Walt get rid of his? He dissolved them in HF. It's not because it's a strong acid, okay? But it's just very caustic towards bodily tissue.
So, also titrate your tissue as well.
Pardon?
Titrate.
Okay.
breaks down tissue.
Oh, Tide. Mhm. Yep.
Well, I have a question that's kind of a little off topic. Since you have watched Breaking Bad,
I've watched it, yeah. many times.
can any chemist actually do what Walt did?
Making meth?
Yeah, like, is it
Yes.
chemistry, person, qualified?
Oh, you would, I shouldn't be saying this, but, you will learn enough skills and techniques in this class, in your laboratory, to almost do what he did. You won't understand how it happened, and you'd probably blow yourself up doing it. But you would know enough chemistry to actually, it's not hard to do. I'm not gonna teach you how to do it.
There you go, there's the legal advice.
But what I will tell you is that many of you have probably actually used meth. I've used meth.
That is-
It's called lev-methamphetamine. It's in Vicks Vapo inhalers. We'll learn about that in another chapter. It's identical to meth in all respects except one, and it's that one aspect that allows it to be legal versus illegal.
So is Adderall.
Huh?
Adderall.
Adderall? I don't know about Adderall.
If you misplace one thing, it becomes an addiction.
Meth? Okay.
Like Sudafed, is that what
I believe so.
Sudafed, yeah, there is a precursor that you can extract out of that to make it. Can't believe we're having this conversation about that. But we really don't have much time left, okay? So we will finish up on the acids and bases stuff on Wednesday, and then we will jump into chapter 3. So everything from chapter 2 up to this point is fair game for a future quiz. I'm not saying we're having a quiz on Wednesday, but we are having a quiz today. And that quiz question that I want you to turn is 1.30. 1.30. So rip it out, put your name on it. Please also put your ID number. And just hand it in on your way out. And I will see you all on Wednesday.
Appreciate it. That's the only one I didn't get to know.
Well, you got a few minutes, you can do one or two.
I don't know, I did some of them, but not that one. Just kidding.
So before you sent that email, I went ahead and already worked out on the back because I forgot I probably should have done that. So I got-
You'll get them back, so you can turn it in if you want.